Introduction to Probability, my favorite chapter. So to start with, a random process is a situation in which we know what outcomes could happen, but we don't know which particular outcome will happen. For example, flipping a coin, rolling a die, putting your music on shuffle, whether the stock market goes up or down tomorrow, etc. And so it can be helpful to model a process as random, even if it is not truly random. So here is an article about how iTunes shuffles your music. And long story short, it's actually really hard to get a computer to generate truly random numbers. And a lot of times they cheat by picking numbers that are not actually truly random. But if we wanted to find the probability of getting, 3 Taylor Swift songs in a row out of a playlist, then it would be useful to model that as being truly random, even if the app that we're using is not actually 100% random. Just because it can be simpler to pretend like it's actually random. So, study of probability arose out of gambling. This is not a huge surprise. During the 17th century, there were a bunch of French noblemen who had nothing better to do with their time and money than sit around and bet on outcomes of rolls of dice. I believe it. And so when a particular question regarding the dice arose, the Chevalier de Mer posed the problem to 2 notable mathematicians, Pascal and Fermat, and thus began the formal mathematical study of probability. And to this day, a lot of our problems involve gambling. Maybe one Monday when we don't have a whole lot to do, I will teach y'all how to play poker or something. But probability turns out to be really, really super duper important for what we're going to be working on in the next few chapters, which is inference. So these are typical questions that we can solve by conducting a hypothesis test, which is going to be chapter 7, probably next semester. But I keep talking about hypothesis testing because that's the big important thing in statistics. Like, everything we're doing this semester is building up to being able to conduct a hypothesis test. So, a certain county has a population that's 50% women and 50% men. A jury is supposedly randomly selected. The jury ends up having a composition that is 40% women. Was there selection bias, or was this just due to random chance? So what we can do is we can figure out what is the probability of getting 40% women on a jury when the population is 50% women. And if that probability is fairly large, then we say, yeah, that probably just happened by random chance. If the probability is really small, then we say, oh, it's really unlikely that this happened by random chance. Maybe it wasn't random. In short, that's a hypothesis test. In a randomized double-blind controlled experiment, a new surgery saved lives 60% of the time, while the old surgery saved lives only 55% of the time. Is this a big enough difference to replace the old surgery with the new one? Again, that's something that we could do a hypothesis test for. So if the 2 surgeries actually are the same, what is the probability that we would see a 5% difference? Is it a really big probability, in which case, maybe the surgeries are, interchangeable, we shouldn't bother replacing it? Or is it a really small chance, which would indicate that actually the new surgery is better and we should replace it? A pack of potato chips is supposed to be manufactured to have an average weight of 10 ounces. 30 random bags of chips are weighed and have an average weight of 9.6 ounces. Is the manufacturer cheating? So, if the bags really have an average of 10 ounces, what's the probability that just due to random chance, we could get 30 bags with an average of 9.6 ounces? If it's a really high probability, then yeah, maybe it was just random chance. But if it's a really low probability, then we start to suspect that something else is going on. So, this is how we use probability for hypothesis testing. So, basic probability, right? So, we're going to roll a fair die once. Our notation here, we're going to use P for probability and the event in parentheses. So this is the probability that you roll a 1. Well, you have 6 outcomes, and one of them is a 1, so you have a 1 out of 6 chance. The probability that you roll at least a 4, right? That's the same thing as a probability of 4 or 5 or 6, which is 3 out of 6 or 1/2. Probability that you roll at most a 2 would be a 1 or a 2, which is 2 out of 6, which is 1/3. We definitely covered this in pre-calc, and you should absolutely know this. Should be pretty easy. Don't worry, I promise it gets harder. Alright, so the most basic definition of the probability of an event is the number of ways an event can happen out of the total number of possible outcomes. So, the probability that you get 2 heads in 2 tosses of a fair coin, right? You could get, so out of tossing a coin twice, you could get heads. You could get heads on the first try and tails on the second try. You could get tails on the first try and heads on the second try. Or you could get both tails. So there are 4 possible outcomes, and one of them is heads. So the probability that you get both heads is 1/4. The set of all the possible outcomes is called the sample space. Sample space. I can spell. One way that we can do this is we can make a tree diagram if listing out all the possibilities is confusing. So the square diagram would be, right, you can get heads or tails on the first try and heads or tails on the second try. And so you get heads, tails, heads, tails, and tails. But if you have more than 2 things, you can make a tree diagram. So, the first time, we can get either heads or tails. And then from each of those branches, we can get heads or tails, heads or tails. And then each of those branches, we can get heads or tails. Heads, tails, heads, tails. So you can follow each path, right? So like heads, tails, heads, tails, tails, heads, tails, tails, heads, tails, 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 heads, tails, tails, tails. And so that gives us our sample space, and it's a nice way to organize things. And when we start talking about Bayes' theorem, this is going to be really helpful. So, tree diagram. So, the probability that you get heads, heads, heads in 3 tosses of a fair coin. There is one scenario where you get 3 heads out of 8 total. But wait, what about things that aren't so easy? So if we take a thumbtack and we toss it in the air, right, it can either land on the point, like in this picture, or it can land on the face, right, something like that. And these are not going to be equally likely. So how would we find the probability of it landing face down? Or how do we find the probability that a comet hits the Earth tomorrow? Right? It's not a 50-50 chance. It's not it happens or it doesn't. How do we find a probability for something that we can't model mathematically, like a die roll or a coin flip? So, the relative frequency theory, the probability that an event occurs is the proportion of times the outcome would occur if we observe the random process an infinite number of times. So, if we threw this tack in the air an infinite number of times, then the proportion, the number of times it lands face down over the number of times we toss it, would be the probability. And hey, if you're in calculus, take the limit as the number of times we toss it approaches infinity. Obviously, we can't actually flip the tack an infinite number of times. But we could flip the tack 10 times or 100 times or 1,000 times, and we could use that as an approximation of the probability. So that would be an experimental probability, where we approximate it by simulation. Right? N is the number of times we repeat the random process. As our n gets larger, the approximation gets better. Right? So the number of successes over the total number of times we toss it will approach the true probability as n approaches infinity. If you're taking calculus, or you took calculus at least through the part on limits, that should kind of make sense. If you're not taking calculus, don't worry about it. So, technically, the law of large numbers says that as more observations are collected, the observed proportion of occurrences with a particular outcome after n trials converges to the true probability of that outcome. I.e., the more times you repeat the experiment, the better estimate of probability tends to get. In your notes, don't just copy this. Put it in your own words. Alright? Basically, the more times we repeat the process, the better our approximation of the true probability. Right? So with the tack, say if I do it 10 times and I get 3 out of 10. And then I do it 100 times and I get 35 out of 100. And then I do it 1,000 times and I get 334 out of 1,000. Let's make it 344. Right? So the more times that I repeat this process, the closer I get to the true probability. And maybe the true probability is, I don't know, 0.3454544 something. Who knows? Right? But the more that I repeat it, the closer I get to the true probability. So, back to the probability the comet hits the Earth tomorrow. Every day we're repeating this experiment, right? So far, a comet hasn't hit the Earth, so the probability is 0? Well, not exactly. Right? The point here, so we're going to talk about Bayes a lot. Bayes was a very famous probability mathematician, and you can blame him for all of the issues that you're going to have in this chapter. But the Bayesian theory of probability says that probability is a statement about our knowledge or lack of knowledge. Probability is therefore expressed as degrees of rational belief. It's a measure of our belief, not a physical property of the world. So, if I say that there's a 0% chance the comet hits the Earth tomorrow because it's never happened before, that doesn't mean that a comet can't actually hit the Earth tomorrow. It's that I believe that it can't. But I could be wrong. Right? Probability is about our belief. If I roll a die an infinite number of times, the probability of getting a 1 is 1 out of 6. I believe that 1/6 of the time I'm going to get a 1. But for any non-infinite number of times, the probability is probably not going to be exactly 1/6, the experimental probability. I'm not going to get a 1 exactly 1/6 of the time. So, it's a measure of belief, not a physical property of the world. And we're going to pause here, and we'll talk about probability rules in the next video. So, think about this a lot. It's really fascinating, actually, some of the stuff that we can do with probability. And, well, if it's a statement of belief, you could argue whether that is meaningful or not. But things like insurance companies move a whole lot of money based on the concept of probability. You know, what's the probability that a tree is going to fall on my car? Or what's the probability that a leak is going to flood my apartment? Or what's the probability that I'm going to break my leg and have to go to the hospital? All of that, you know, the amount of money that I pay for car and renters and health insurance is based on what somebody calculated as those probabilities. And then the expected cost of dealing with those situations. So, probability, not totally useless.